This video is what is chemistry? So try to list as many fields of science as you can. So how do all of the fields that you listed fit together? Well, they're all types of science, and science can be divided into 3 different groups. So we have formal science, which includes mathematics and logic, humanistic science, which includes psychology and sociology, and then we have natural sciences, which include physical science, which is physics, and chemistry, what we're concerned with, and life science, which is biology and environmental science. So look at the list that you made and try to classify it, each of the fields that you used, as either formal, natural, or humanistic science. So how can we further classify chemistry? There are 5 main types of chemistry that we're going to talk about. The first one is analytical chemistry. So this is the study of the composition of matter and what things are made of. Then there's biochemistry. This is the study of chemicals that are found in living things. Inorganic chemistry is the study of chemicals that do not contain carbon. And organic chemistry, the study of chemicals that do contain carbon. And physical chemistry, which is the study of mechanisms, rates, and changes that occur during chemical reactions. So why should we study chemistry? Chemistry explains the natural world. It can prepare you for your career. So no matter what career you go into, you're going to have to deal with some kind of chemicals. Chemistry helps you become an informed citizen. Chemistry will make you a better cook. Chemistry teaches you skills like logic, reasoning, and problem solving. And finally, chemistry is just awesome. So think about it. How might you use chemistry in your career? This video is on the scientific method. So what is the scientific method? Typically, it's a series of steps that are used to investigate a problem. And it's not necessarily a linear prescribed method, so you may have to go back and repeat different steps at different times, depending on your results. It is process-oriented and adapted to each experiment. So take a minute. How have you used the scientific method? What are the steps? The first step is to identify the problem. Then you'll collect information, form a hypothesis, figure out a way to test your hypothesis, then based on your results, accept or reject your hypothesis. If it's right, try it again. If it's wrong, make a new hypothesis and start back over from there. Finally, report your results. Even if your results don't support your hypothesis, it's really important to report them because somebody may be able to use your methods for their own experiment. So the first step, identify the problem. State a very specific problem that needs to be addressed by your experiment. Then, collect information. So gather information about the problem from reliable sources. Very, very important that they are reliable sources. So how do you know if a source is reliable? Peer-reviewed articles, If it's a web page, you need to look at who is in control of that information, and was it a paid study? So which of the following would be a reliable source of information? So your chemistry textbook or a scientific journal. Your next step is to form a hypothesis. So based on your observations and research, propose a testable and specific solution to the problem. Then test your hypothesis. Design an experiment with step-by-step procedures. It's very important that your procedures are step-by-step because you want to make sure that you are able to repeat your procedure and test your hypothesis more than once. When you're designing your experiment, you will have different variables. A variable is any factor that can change an experiment. So there are two types, independent and dependent. Independent is purposely changed, so this is what you're testing. Dependent changes because of your experiment, so this is your results. There are also controls. So these are something that you don't change so that you know if your experiment or what you tested caused the result that you wanted. So it's used for comparison to experimental groups and can help eliminate the effects of confounding variables. The next step is to accept or reject your hypothesis. So determine if your results support your original hypothesis. If not, reject your hypothesis. This may lead to more research being done or your hypothesis being amended or changed. Finally, report your results. Even if your end result was that your hypothesis was wrong, you should still report it. Someone else may read your report and conduct their own research. So what are the minimum requirements for something to be a scientific process? This video is a review of the math that we are going to use in chemistry this year. So the first thing is the order of operations. So we use parentheses, exponents, multiplication and division, addition and subtraction. You can remember that by please, excuse, my dear, Aunt Sally. Parentheses, exponents, multiplication and division, addition and subtraction. So the first thing, if we're looking at this first problem, first thing we have to do is look at the exponent. So 6 squared is 36. Then we just have addition and subtraction. So these we would do in order. So 4 plus 7 is 11 minus 36 plus 3. 11 minus 36 would give us negative 25 plus 3 equals a negative 22. Okay, for the next one, the first thing we have to look at are the parentheses. So we have 11 minus 5 cubed plus 50. The next thing would be our exponent. So we have 50 plus 5 cubed is 125 minus 11. 50 plus 125 is 175 minus 11 equals 164. Okay, the next one, this is all addition and subtraction, so we just go in order. So we have 58 plus 2 is 60. 60 minus 4, 56, plus 5 gives us 61. Okay, and whenever you have a division symbol, it's like saying these are in parentheses. So we have 2 times 2, or 2 squared, so 4 plus 5, so the bottom equals 9, and we have 72 plus 63, which equals 135. So 135, now divided by 11, equals 15. So remember that multiplication and addition are commutative. So this property says that the order that we add and multiply doesn't change the answer. So 2 plus 3 or 3 plus 2, they still both equal 5. But subtraction and division are not commutative. If you change the order, then you're going to change the answer. So let's look at these. Which one is not like the others? So x times 12. 12 times x is the same thing. Still 12 times x. Here we have 4 times 3x. That equals 12x. X times 12. Still the same thing. X times 12, still the same. 4 times 3 is 12x. Now this one we have 2x squared. So that would give us 4x squared times 3. That would give us 12x squared. We have 3 times 4x, which is 12x. 4x times 3, still 12x. 4x times 3, and 4 times 3x is 12x. So this is the one that is not the same. Okay, next we have ratios, and we're going to use ratios a lot this year. So ratio is a comparison between two different things. In chemistry, we'll compare the amounts of reactants to products. So for the equation above, there are 2 oxygens for each carbon dioxide that is produced. So we could write our ratio of carbon dioxide to oxygen, or oxygen to carbon dioxide, as 2 to 1. So if the ratio of blue to green marbles is 3 to 4, how many green marbles are there if you have 350 marbles? So next we have simplifying fractions. To simplify fractions, you divide both the top and bottom by the largest number the numerator and the denominator have in common. So look at the first one. We have 40 and 48. So 8 will go into both of those. If we divide 40 by 8, we have 5. If we divide 48 by 8, it's 6. So that would be 5/6 is a simplified fraction. For number 2, 8 is the biggest number that would go into both of them again. So if we're going to divide each one by 8, we would have 1, and 72 divided by 8 is 9. To rearrange an equation, you must isolate the variable that you're looking for. Whatever operation is being done to the variable, you use the opposite. So if it's addition, you subtract. If it's multiplication, you divide. If something is added to the variable, you would subtract that from both sides of the equation and solve for x. So the first one, we're trying to get x by itself. So to get rid of a plus 2, we would subtract 2 from each side. So those go away, and x is equal to 7 minus 2, 5. Okay, we're trying to get x by itself again. So first we have to get rid of the plus. So we're going to subtract y from both sides. So this gives us 2x equals 16 minus y. Now we have to get rid of the 2. So since it's multiplied, we're going to divide. And so we'll divide the whole side by 2. So we have x equals 16 minus y divided by 2. Okay, in this one we're trying to get, again, x by itself. So we have multiplication, so we need to divide by y on each side. So x equals a, b, c divided by y. So in science, we use the metric system. So let's look at the metric system, or the system that you're used to, the standard system. So we measure mass with ounces, pounds, and tons. 16 ounces equals 1 pound, 2,000 pounds is a ton. So we use the metric system. This allows scientists around the world to communicate with a standard system of measurement. The metric system is based on the unit 10. So unlike the standard system, everything is based on a unit 10, and different units are named by just adding a different prefix. So in the metric system, we're going to use meters for length, liters for volume, and grams for mass. So King Henry died by drinking chocolate milk is a way to remember all of the prefixes of the metric system. So King stands for kilo, Henry is for hecto, died is for deca, by is for the base unit, so meter, liter, or gram, drinking is for deci, chocolate is for centi, and milk is for milli. So as we go larger in the metric system, we're going up by 10 every time we move through a block. So a decameter would be 10 meters. A hectometer would be 100 meters. And a kilometer would be, or kilometer, would be 1,000 meters. If we're going the other way, a decimeter would be 0.1, a centimeter 0.01, and a millimeter would be 0.001 meters. If we're going to convert 22 decaliters to millimeters, we're going to multiply the number if you're getting smaller. So we're going smaller, so this means moving the decimal one place to the right every time, for every one we go. So we're going to start at decimeter, decameter, and move 1, 2, 3, 4 places. So we can add in zeros. So 22 decameters is equal to 220,000 millimeters. This video is about accuracy and precision. This is something we will cover in class, but if you missed it, then here's the video. So accuracy is how close a measured value is to the actual value. So this is, are you getting what you should get? Precision is how close each value is to the other values. So if we look at this target, we can see what this means. So if we're looking for something that is accurate but not precise, it might look something like this. We have targets. It's near the target, but none of the darts would be next to each other. if it's precise but not accurate, they're all very close to each other, but it's not close to the target. If we have both accurate and precise, our measurements would be close to each other and close to the target. And if we have neither, they could be all over the place. So how can we make sure that our measurements are accurate and precise? And so the first way is to be careful and take your time. Double check your measurements and take care of your equipment. Repeat your measurements, so measure things more than one time. And always estimate one extra place for each measurement. So if we're looking at this pencil and we're measuring it, it's between 5 and 6, so we would use our best guess of what this is, so we could call it 5, which we know, plus one extra place would be 5.6. It's very important you always estimate that extra place. So Jalen, Travis, Juan, and Alexa are measuring a notebook. The actual size is 28.3 centimeters. If each student measured the length 4 times, their results are shown below. Determine if any of these measurements obtained are accurate, precise, both, or neither. So starting with Juan, would this be accurate or precise, or both, or neither? So 28.3 was the actual measurement. They're all very close to 28.3. They're also all very close to each other. So this would be accurate and precise. Travis, his 4 measurements are all close to each other, but they're not close to the actual. So that would be just precise. Jalen's are all very close to each other. They're also pretty close to the actual measurement. And Alexa, hers aren't really close to each other or close to 28.3. So neither. This video is on significant figures. So significant figures are very important in chemistry because they determine how we measure things and show us how accurate our measurements are. So we have 5 rules for determining significant figures. Rule 1, all numbers that are not 0 are significant. So anything that isn't a 0 is always going to be significant. So in this first example, we have 4 significant figures. In example 2, we have 5 significant figures. Rule 2, zeros between non-zeros are always significant. So this means any sandwich zeros. So these two are in between non-zero numbers, so they're significant. So we have 1, 2, 3, 4, 5, 6 significant figures in this number. These 3 zeros are between non-zero numbers, so we have 6 in this one also. Rule 3, leading zeros are never significant. So if there's a 0 in front, those are never going to be significant. So this number just has 2 significant figures. So these leading zeros, they're just there for a placeholder. So we have 2, and this number also. Trailing zeros are significant only if there's a decimal point. So the first example, number 7, we have 2 trailing zeros, but we don't have a decimal point, so these are just there for place value. They are not significant. So we have 2 significant figures and this number. Over here we do have a decimal point, so that means that these are significant, and all 4 numbers are significant figures. And our last rule, Rule 5, exact numbers or counting numbers or conversion factors have an unlimited number of significant figures. So when we're using sig figs in calculations, when doing calculations, there are different rules for different operations. So for addition and subtraction, the answer is going to have as many decimal places as the fewest number. So if we had this, our answer, we would look at our decimal places. This one has 2 decimal places, this has 1. So our answer needs to have 1 decimal place. We go by the fewest. In multiplication and division, the answer has the same number of significant figures as the least number, the number with the least. So if we had this example, we would look at the total number of significant figures. There's 4 in the first number and 2 in the second number. So our answer needs to have 2 significant figures. So when you're doing calculations, it's important to remember to follow the order of operations. So use the rules for addition and subtraction and multiplication and division, depending on what operation you're doing. If the next operation has the same rules, so you multiplied and then you divide, don't round yet. Continue solving the problem. If the next operation has different rules, like multiplication and then division or addition, round the answer before you go to the next operation. So determine how many significant figures are in the following. The first example, these are all leading zeros. Leading zeros are never significant, so we only have 2 significant figures. In the next example, these are trailing zeros, but there's no decimal point, so again, we have 2 significant figures. We have trailing zeros in the third example, but this time we do have a decimal point, so that gives us 4 significant figures. And in the last one, we have trailing zeros after a decimal point, so we have 5 significant figures. This video is about scientific notation. So use scientific notation because it allows us to easily use very large or very small numbers. So in chemistry, we use many extremely large numbers and small numbers. For example, instead of writing this out every time we need to use it, we could write 6.022 times 10 to the 23rd. So this number is an example of standard notation, the first one. That's what we're used to. The second number here is an example of scientific notation. So in scientific notation is a special way of writing numbers using exponents. So with scientific notation, you'll have one number before the decimal point, times 10, always times 10, and then to a power. or an exponent. So standard notation can be converted to scientific notation by moving the decimal to the left or to the right. The direction and the number of times the decimal is moved determines the sign of the exponent and the power. If you move it to the left, it's positive. If it moves to the right, it's negative. So circle the numbers that are written correctly in scientific notation. Pause the video here and write the ones that are correctly in scientific notation. So to convert from standard notation to scientific notation, the first thing you do is move the decimal point so that there is only one number from 1 to 9 to the left of the decimal. So our decimal starts here. We need to move it here. Then we're going to count the number of places that the decimal moved. This is going to be our exponent. So 1, 2, 3, 4, 5. So we have 4.51268 times 10. We moved 5 places, and then we look to see if we moved left or right. We moved to the left, so our exponent is going to be positive. So this would be the correct scientific notation. All right, for the second one, our decimal is here. We have to have one number in front of the decimal. So this time we moved 1, 2, 3, 4, 5, 6 places. So we have 2.1548 times 10. We moved 6 places. Now, did we go left or right? We went to the right, so our exponent is negative. Same thing with the next one. We're moving 1, 2, 3 places. Times 10. We went right, so it's negative 3. So we can convert from scientific notation back to standard notation. So to do that, we're going to look at the exponent first. So this is the number of places that you will move. So for this one, we're going to move 6 places. Because it's a negative, since it's negative, we're moving to the left. So we started out with 1.2. We're moving 6 places left. 1, 2, 3, 4, 5, 6. Now, any places that we don't have, we're going to fill in with zeros. So that would be our number in standard notation. We'll do the same thing for the next one. 4.35, we're going to move 3 places. This time we're going to the right because it's positive. So 4,350. Okay, we're moving 8 places to the left. 1, 2, 3, 5, 6, 7, 8. And then we add in zeros. Finish the last 2 on your own. And that is it for scientific and standard notation. This video is about lab safety, the rules in the lab, and the equipment that we will use this year. So staying safe in the lab. If you break something, inform your teacher immediately. Your teacher will clean up any broken glassware. Broken glass must be disposed of in the broken glassware container, not in a trash can. When disposing of chemicals, never pour chemicals down the drain unless the lab handout explicitly says to. Not all chemicals can safely or legally go down the sinks, so it's very important to dispose of any chemicals in the proper place. When you're adding acids to water, you always add the acid, never add water. If you add water, it can cause it to boil, and the acid can splash out. So always add acid. If there's a fire in the lab, don't assume that water will actually put the fire out. In some cases, it can make it worse. Sand is a very good option for a small fire. The fire extinguisher is always your best option though. If there's a fire, remember, pass. So pull the pin, aim at the base of the fire, squeeze the trigger, sweep back and forth slowly. This is the acronym for using a fire extinguisher correctly. If there's a spill in the lab, inform me immediately. We'll need to use different chemicals to clean up the mess depending on what's spilled. If you spill a chemical on you, you must wash under the safety shower for at least 15 minutes. When heating different things in the lab, never mix hot and cold when using glassware. The extreme temperature change can cause the glass to break. Remember, the glass is going to look the same whether it's hot or cold, so be cautious. Some of the safety symbols you should know are flammables, corrosive, irritants, oxidizers, gas under pressure, carcinogen, mutagen, or teratogen, explosive, environmental effects, and acute toxicity or fatal. So hazard means that something is harmful or dangerous. Acute toxicity means immediately poisonous and avoid all direct contact. Oxidizing means that it will react violently with fuel sources and metals. Corrosive literally means having little teeth. It eats away at other materials. Acids and bases are good examples of corrosive materials. And teratogen means causes birth defects. So some lab safety equipment we'll be using include fire extinguishers, safety showers, eye wash, goggles, lab aprons, and gloves. Some of the glassware includes petri dishes, separatory funnels, test tubes, Erlenmeyer flasks, graduated cylinders, beakers, glass funnels, glass bottles, volumetric flasks, and round bottom flasks. We'll also use crucibles, clay triangles, evaporating dish, and mortar and pestle. We'll use Bunsen burners, strikers, and tongs, burettes, balance, thermometer, pH meter, bulb, pipette, ring stand, wire gauze, well plate, stopper, Buchner funnel, ring clamp, wash bottle, test tube rack, flask brush, test tube brush, glass stirring rod, scupula, eyedropper. This video is about density. Density is the ratio of an object's mass to its volume. The formula for density is D equals M divided by V, where D is the density, M is the mass in grams, and V is volume in milliliters or centimeters cubed. Different objects are going to have different densities. Higher density objects are going to sink, while lower density objects are going to float. So look at the list below. Using the densities of these liquids, place each one in the correct place in the cylinder to the left. So the lowest or the highest density, which would be at the bottom, is honey, followed by corn syrup, Dawn dish soap, water, vegetable oil, lamp oil, and finally, rubbing alcohol. So what is the mass of a block that has a density of 2.49 grams per milliliter and a volume of 1.25 milliliters? So the first thing we have to do is write down our formula. Density equals mass over volume. We know the density, 2.49, equals the mass, which is what we're looking for, divided by 1.25 milliliters. So, to solve for m, we're going to multiply each side by 1.25 milliliters, and m equals 3.1125 grams. We need to remember our significant figures. So this is multiplication. We need 3 significant figures. So our mass is 3.11 grams. So the next question, what is the density of a marble that has a volume of 1.25 centimeters cubed and a mass of 0.75 grams? So we're solving for density, 0.75 grams over 1.25 centimeters cubed So the density equals 0.6. We need 2 significant figures, 0.60 grams per centimeter cubed. So these are particle diagrams. So if we had these 3 images, which one would have the lowest density out of the first one? So that would be this one. Okay, so in this example, they all have the same mass, but they have different volumes. So which one would have the highest density? Would be this one.